start talking about slotted eGraphs. The basic idea is slotted eGraphs are eGraphs with name binding built in. And so maybe I want to start off the talk by talking about name binding first. And yeah, there we go. So I have four very, very different terms on the slide, involve four very, very different languages. We have lambda calculus, then we have something like linear algebra, we have predicate logic, and we have Python. And like, whatever language you're working with, it's probably something that has some of these features, right? It's somewhere in there, probably. And the point that kind of connects all of these four languages is they all have name binding. So they all have a feature that introduces a local variable like this I, and its meaning is only defined by being defined by this symbol, and it's only usable in the body of that symbol. This kind of name binding, it's enormously universal. Most languages kind of have some form of name binding. Louder, you mean? Okay. Okay, yeah, sure, okay, yeah. Yeah, so most languages have some form of name binding, so the takeaway from this slide is really just name binding is kind of everywhere. So, now comes the bad news. eGraphs are not that great at doing name binding at this point. And let me motivate this by an example. And for that, consider these two terms. These two terms are pretty easy and quite similar. F of x and y, and f of x prime, y prime, right? So these two terms have the same function, f, and they kind of only differ by having slightly different names of the variables. So it's x versus x prime and y versus y prime. But they're kind of conceptually the same idea, right? If you want to store this in, for example, an eGraph, this is like the perfect use case for sharing. Because like whatever property holds for f of x and y will certainly also hold for f of x prime and y prime, right? Any property will definitely translate from one to the other because it's the same term just with a different name of variables. So perfect use case for sharing. But now if we actually put this into an eGraph, we'll see, well, there's no sharing at all. So in the first slide, we see f of x and y, and then we see f of x prime and y prime, and we see there's nothing shared. So whatever property we have in one or the other, they will be stored completely separated from each other, and there's no sharing. And that's a problem. Because what this means is that when you rename variables in your eGraph, what you're basically doing, you're opening a kind of parallel universe of your eGraph where you kind of store everything separately. Because just one name is different, you have to copy all the stuff and just do the different kind of sub-eGraph. That's super costly. We don't want to do this, right? Any rewrite rule that will just rename things will break sharing, and that's a problem. Now, you might say, well, why don't we just use De-Bruijn indices, right? Isn't this kind of the solved problem? De-Bruijn indices solve the renaming problem, so let's just use them. And I think this is partially true, but there's still a problem with using De-Bruijn indices. And I can show this problem using this example. This is a term in De-Bruijn indices, and you can see we can actually do better reduction on it. So we have a lambda expression here, lambda, and it's applied to an argument. So what we can do is we can actually call this lambda and actually compute it through, and using better reduction, and this is what comes out. So we just plug the argument in there, replace this %0, which is the innermost De-Bruijn binder, and we get the simplified version. And what we see, there's another side effect that happened here, which is that we actually also renamed this f of %1 to f of %0. This is also what happened. And that just happens because a binder was removed, and thus we had to shift the index. Because that's what the De-Bruijn indices are, right? You just remember how many indices you have to go out, how many binders you have to go out. Thus, when you remove a binder, the indices have to change. And now this is the same problem as with renaming. Shifting these indices is kind of breaking sharing, right? There's no sharing between f of %1 and f of %0. They're just completely different things to an eGraph. So when this happens, you break sharing, and you again open the subuniverse, which is a problem. So in De-Bruijn, adding or removing binders also breaks sharing. Kind of the same problem as before, just in a different scenario. Right, so that's the problem. And now let's talk about how we maybe want to solve that problem. And that's where slotted eGraphs come in. And I want to start off by the same example we've seen before. F of x and y, which is one term, and then the other term, f of x prime, y prime, where there's no sharing. This is a normal eGraph at this point. And now how to make this slotted is we have to apply the following key idea. We want to unify e-nodes that are equivalent up to renaming of variables, right? We want to merge things that just have different names but are conceptually the same. And we want to unify them into an e-class which is parameterized by its variable names. So what does this mean in practice? In this case, we have 4 variables right here, right? So these are 4 e-nodes. And all of these e-nodes are equivalent up to renaming of variables because they are variables, right? If you rename them, they will be the same. So what the key idea tells us to do is we should unify these four e-nodes, for variables, into a single parameterized e-node, or parameterized e-class. And this looks as follows. We now have all of these four have been merged into one e-class, and this e-class now has a header. This header says, hey, we have a parameter v here, and we're kind of a generic e-class. We're generic over the parameter v, and then we just have this one e-node which says, hey, I am the variable v. And what this now means is, whenever we invoke this e-class, we have to give it an argument, or we have to plug into this parameter v. So in this case, f of x and y, we just have to put x into it and y into it to represent what we wanted, and here, x prime and y prime. Now you might wonder, okay, what are these great things there? We don't know these. And these are slots. So if you see these things, they're not e-nodes, they're not e-classes. This is kind of where we kind of diverge from normal e-graphs. This is the new thing. These are slots, and they really just represent the concept of a variable name. So something that you can rename that has no kind of global meaning, but just makes sense in a local setting and is a bound name. Right. So, and we will always show them in gray. So whenever you see something in gray, you know it's a slot. And it's this new kind of weird thing. Cool. We're not quite done here. We still have more unifying to do. So there's still e-nodes that are equivalent after renaming of variables that we have not merged, right? F of x and y, f of x prime, y prime, they're still kind of the same, just with different names. So again, we should unify them into a single e-class that is parameterized by these names. So let's do this. We merge it, and the x and y become a and b, and x prime and y prime also become a and b. So we converge them together into one generalized e-class, which is now parameterized by these arguments. Cool. So now we actually made it a slotted e-graph, and it's much smaller, which is great. But you might wonder, okay, how do you actually conceptually think about this object now? Right, I think there's a good intuition for how e-graphs work, but what's the intuition behind this? And so let's first talk about what is actually an e-class conceptually. A normal e-class is kind of just a set of equivalent terms. So that's what it represents. That's the idea behind it. Right, it's just an equivalence class, a set of equivalent terms. And because we now added this layer of parameterization, a slotted e-class is actually a function that accepts variable names and then yields a set of equivalent terms. So it's the same thing as before, just with a new parameterization added to it. So now, slotted e-classes are really just functions. And what we can do with functions is we can call them. And that may be helpful to see how it actually works. So we can call this function, this class, this function, with, for example, the names x and y. And we will see that it will yield the set of terms, of equivalent terms, in this term just one, because it's quite a boring e-graph, f of x and y. And this really just happens by passing x and y through, see where this goes through, and then we see what the result will come out to be. So e-class, slotted e-classes really are just functions from the parameters and to an equivalence class of terms. That's the basic idea. Now we can also call this function, for example, with x prime, y prime, and we get f of x prime, y prime as output. And that's great, because now these two terms were the original ones that weren't shared before, but now they are apparently shared in this e-graph, Yeah, that's wonderful. So better sharing at this point. So this is a talk about name binding. And at this point, I didn't even talk about name binding, so let's fix that. And talk about how we do actually binders in slotted e-graphs. And we'll do this by an example, which is, that's a bit too quick, by an example which is, again, lambda calculus. So you can really think about this as being a big sum or kind of a quantifier or whatever binder you like to think about, but we'll just pick lambda as an example here. And we'll concretely map the identity function in lambda calculus in a slotted e-graph. And it looks as follows. So this might look pretty similar to what we've seen before on the previous slides, but there's one difference. It's this thing. There's a new e-node type, which is this lambda e-node. And it introduces a slot called x, right? And this slot x we directly use to call the variable e-class, which corresponds to the fact that this, the body of this lambda is actually just the variable itself. And so we just plug it in there, and this corresponds to the body, right? There's one important thing here, which is that because now this variable x is bound by this lambda e-node, it's actually not part of the parameter list, right? Because this is now a closed term, it doesn't need to depend on anything, it's completely independent. Yeah, and what this also means, if we now call this class as a function again, it doesn't only return lambda x dot x, but also all the renamed versions of it, right? We don't want this to store all the different namings of it. That doesn't make sense. That's exactly the problem we want to solve, and that De-Bruijn also solves. But so whenever something is not in the parameter list anymore, it's kind of automatically, you can think of it as it means this thing and all other names that you can think of. So this kind of covers all these things automatically. Yeah. Cool. That's the basic idea of how slotted egraphs work. Now, there are a few more challenging situations where slotted egraphs kind of are a bit harder to do. And I want to kind of talk about these more challenging situations and how we solve these situations to still kind of get the stuff to work. And let's start with the first one. And it talks about this slotted egraph. This slotted egraph talks about terms that of the form x times 0. So a variable multiplied by 0. Well, there's something we know about x times 0, which is it's 0. So what we would like to do here, we would like to unify x times 0, so this e-class. Well, I'd like to unify this with 0, this e-class, which makes sense, right? That's true. And now here's the problem. The resulting e-class, does it actually depend on x, or does it not depend on x? Because one class says clearly it should depend on x, and the other says no, it should not, right? And so we have to make a decision, should it depend on x and should it not? And I think there's many sound, or definitely also unsound ways to do this, but the choice we made is to say it actually does not depend on x, right? This thing is 0, this thing is also just 0, it literally does not depend on x. Or if this is y or something else or anything, multiplying anything by 0 is 0, so we can remove the dependence on x and generate this new e-graph as an output. So we do not depend on x anymore, and we've merged these e-classes now. Now there might be a weird thing in the slide, which is, well, there's still an x. And that might confuse you for a minute. And this x is very similar to what we've seen before with the binder. Right? In the binder slide, you saw also a x that was not part of the parameter list because it was bound by the lambda. Here it's a bit different because it's not bounded by the lambda, but still it's not the parameter list. And what this now means is what I've alluded to before. This e-class represents 0 because, well, 0 is in there, and it does represent x times 0 and y times 0 and z times 0 because it's not connected to the actual name. It does not really matter what you plug into this. This is redundant. This is not important. Anything that you plug into this actually will yield 0 in the end anyway. So you can actually get rid of the name, and this again then corresponds to plug in any name of this, and it's all the same. And also for completeness, this is a recursive class, so there's also some fancy recursive terms in it. Okay, yeah, cool, that's the first challenge. There's a second challenge, which talks about this e-graph, and this just corresponds to a plus b. So right, this is an addition of two variables, and this is what this talks to. And now there's another property we know about a plus b, which is, well, a plus b is equal to b plus a. Why do we know it's symmetric? And now, so what we would like to do is we would like to merge the e-class of a plus b with the e-class of b plus a. Now we're at a problem because, well, they're actually the same e-class already. So that's kind of hard to do, right? But still, we still want to kind of get this information across that this is actually a symmetry. We need to encode this somehow. And so now what we need to do is we need to extend our feature set a bit to allow e-classes to be symmetric somehow. And how we do this is we say, we have this fancy feature up here, which says e-classes are not only depending on one parameter list, a comma b, but actually a set of parameter lists. So what this means is, however you call this with a comma b or with b comma a, all the stuff that comes out of it is equivalent anyway. So it doesn't matter whether you flip its arguments, it's the same output anyway. And when you think about this again as a function, if you call this with x comma y, you can think of this as being called in this direction, which then yields x plus y, or you can think about this as calling this, which then returns y plus x. So this is just saying, because of the symmetry that we have within this class, actually both things are valid, and all of this is represented by the class. Right. So this was the second challenge, and now we can, oh right, one thing I forgot. One cool property is that this thing can be nicely represented as a permutation group, which actually makes a lot of things pretty nice and I think efficient. Yeah, so that's a dope thing I wanted to mention. But yeah, now we actually come to the evaluation. And yeah, we evaluated by doing reverts on the RISE language. RISE is a functional data parallel language presented at ICFP 2020. And what we did is we compared against the name and the De-Bruijn implementations from Thomas Koehler's PhD thesis. And we also took the rewrite problems from this thesis, right? So we kind of compared against him, his implementations. Right, and to ensure a fair comparison, we backported an optimization to stop unnecessary propagation of substitution, because this made a big impact, and so that we kind of we're not actually comparing any optimizations, but really only De-Bruijn versus slotted. Yeah, that's why we kind of backported this thing. Cool, so let's look at the data. We have a diagram here, and we see named and De-Bruijn in orange and brown, and we see our implementation slotted. The y-axis here is the number of e-nodes that were necessary to solve the problem, and it's a log scale. Right, so there's 3 problems here. There's reduction, which is really lambda calculus, do a bit of beta reduction, and there's not really a big search space, so it's not a hard problem. And you see that all implementations kind of are in the same ballpark of kind of size. So it doesn't really make a difference. De-Bruijn has a bit more work to do, so it's a bit bigger, but yeah. Then binomial is a pretty hard problem, and we see that named wasn't able to solve it. But we see that De-Bruijn and slotted are kind of, oh, again, pretty similar, right? I mean, it's not even factor 2 in difference, so yeah, not really a big difference. But then when we look at the third one, fission, we see a drastic difference. You see this is more than a factor of 100 in size of, in size of e-node count, which is enormous. And you might wonder, hey, why is this discrepancy there? And the reason for that is really, or that's what we think, which makes sense to us, is that the fission problem makes heavy use of rules that introduce binders. So exactly the thing where De-Bruijn breaks sharing, right? The map fusion rule, for example, is a rule where we have 2 maps that are combined to one, which then introduces this lambda, important thing, breaking De-Bruijn's sharing guarantees, right? And then we have map fission, which is the opposite, and it again introduces a new lambda, also again breaking De-Bruijn's guarantees. So in these problems, these rewrite rules were not really relevant for binomial. So this is where the impact isn't really big there, but it is big here. And to really bring the point home that kind of introducing and removing lambdas is the thing that destroys De-Bruijn, we did one more thing. To all of these problems, we added eta expansion. A quite simple rule, but still very explosive. Whenever you have a function, you can represent it as a wrapper function that just passes its argument along to the child. So that's, you can do this, and this is equivalent, but obviously you can do this for all f. So this is a lot of blow up. And it's typically something you avoid because it's very explosive. And now if we do this, we see named and De-Bruijn are not able to solve any problems at all, because in both cases, these creations of new binders are destroying everything, pretty much. And slotted, I mean, there's still a notable cost, but you see it's able to cope much, much better with this introduction of new binders. It's doing all right, I think. So yeah, so I think really introducing and removing binders is the problem that really kind of sets De-Bruijn and slotted apart. Okay, now we come to the state of the implementation. Right? What do we currently do? And so what does currently work? And you currently can specify your own language. This means our implementation is already generic over a language, and also you can define your own binders. You can define quantifiers, you can define a sum, whatever you want in your language, put it into the eGraph, in the slotted eGraph, and then do your stuff. Also, we have e-matching and rewrite rules, so you can really kind of define your languages like your rewrite rules like you want to with patterns, which I think is pretty cool. And one also cool fact is when kind of comparing this to De-Bruijn or named, in named you always have to think about naming collisions, which is really annoying and problematic. And in De-Bruijn, you have to do all these shifts. Here, I think you can really kind of just take the named rules and just forget that you need to do naming collisions because it's just handled by the data structure. So you can really take the named rules and it just works. And you just remove the things that do naming collision. And that's pretty dope, I think. Then we have extraction, which is only working for tree right now. So we don't have DAG extraction at this point, but I think it's possible to do. And we implemented both challenges. So implement the solutions we've mentioned before. Right, but obviously there's also things that are not that yet. We don't have egress analysis, we want to get there, but yeah, we didn't manage to get this yet. Also, there's really no fancy optimization, so our e-matching is very bare bones. There's no kind of performance thing in there. It's taken a while, but there's a lot of kind of headroom for improvement. And yeah, generally it's work in progress, right? It's very fresh. We just made this. So a lot of sharp edges on things we want to improve later on. Still, feel free to check it out. It's on GitHub. And yeah, I would really be happy if someone tries out their language and kind of sees whether it works for them. Would be super cool to talk about it. Yeah, and I think that's my talk. And I'm open to questions if we have time for that.
Thank you for the good talk. We have time for 1 or 2 questions while the next speaker gets set up. Just sort of go in order.
Hi, great talk. One of the things I really loved about that eta reduction example is that you take something that really doesn't saturate in traditional equality saturation and then turns it into this little finite recursive cycle there. That's really cool. Something else that was, I think, more implicit in the symmetric example was this notion of some of the names have these implicit constraints that, oh no, this name actually encodes a different quantity than this other name. And I'm wondering, how have you made that more explicit in this work, as opposed to...
You mean like, in what sense do you mean a different property? Do you mean like different types, or?
So let's say in the symmetric example, I can have A and B and B and A, right?
Yes.
But if I were to then say like, do a congruence, and I could then show that, or I have some other axioms that might accidentally imply that A does equal B when really I want these things to be different.
Yeah.
Can I end up showing, or like in an E-graph, collapsing these two things down to the same thing?
So if you actually show that, in some cases you can kind of prove that all variables are the same because the variable doesn't matter. This is kind of what happens in the x times 0 example, where kind of all variables collapse into one because we see that the variable you put in here does not matter at all. Yes, so this happens.
Okay, thank you.
Many thanks for the great talk. On the symmetry side, I was wondering for the cases in, let's say, lambda calculus where you have, let's say, let commutativity. For example, let x equal something, let y equal something, and for example, let z equal something, and all of them are independent of each other. So there is a kind of symmetry notion there, which is kind of a combination of symmetry with binding. So do you handle those cases as well?
So, I mean, we didn't implement like the let commutative you're mentioning, but I think there's also the problem that like the first let could kind of introduce something that's used in the next let. So there's kind of only a conditional commutativity, I think. So I think it's not quite easy, but I think if you just define the rule and remember to kind of check this, then it should just do this thing. So yeah, I think it doesn't. This is not like only for addition, right? You can put anything into this, and yes, so this should also work if you use this with let bindings. Yeah.
Okay, thank you.
Okay, I think we need to wrap it up and move on to the next speaker. Thank you so much.
Sure.
Okay, next up, Shadaj will be telling us about relational contextual equality saturation. You'll notice this is the third or fourth time that contextual problems have been brought up, so very interesting to see yet another perspective on this problem.